Welcome to our discussion on real population growth, or basically exponential growth. All right, let's start off with an example. If we know the average annual growth rate for anything, and in this case, a world population since 1650 has been about 0.7%. Make sure you pay attention to that, right? That makes a huge difference. However, the annual rate has varied significantly, which makes sense, right? It fluctuates. There were a lot of births after each of the world wars because everybody, felt like they wanted to repopulate. And then, of course, during times of war, there were less children. So it makes sense that it's fluctuated. It peaked at about 2.1% during the 60s. You all know what was happening in the 60s, and is currently, as of 2013, about 1.1%. Find the approximate doubling time for each of these growth rates. So basically, we want to figure out how long does it take for the population to double if it's growing annually at 0.7%, 2.1%, or 1.1%. And if we remember before, there are approximate things for that, right? 70 over the growth rate. So 70 over 0.7, 70 over 2.1, and 70 over 1.1 give you approximate answers for each of those three, 100 years, 33, and 64. But we then found out that there are more precise ways. Instead of these approximate things of 70 over p, we can actually calculate them with the true growth rates of using logarithms, right? But if we're going to use these approximations and we want to predict the world population in 2050, we have to use that the new value is the initial value times 2 to the power of t over the doubling time, right? So t is how much time. So if we assume this video is taking place in 2013, then from 2013 to 2050 is 37 years. And if we use the kind of the overall growth rate that we've seen over a long period of time of 0.7%, and excuse me, and that gave us 100 years as how long it took to double. We put that in, and we see that we go from 7.1 billion in 2013 to roughly 9.2 billion in 2050. If we use that peak growth rate of 2.1%, we end up getting 15.4 billion. And if we use the current in 2013 growth rate of 1.1%, we get 10.6. Some definitions. Overall growth rate is, we've seen this before. We've seen actual or absolute blank and then relative blank, right? We've seen actual growth rates and then relative growth rates. Now we're just doing it in terms of people, whereas in other examples we've seen it in terms of money, right? So actual or overall growth rates is always going to be your total change over time. In the case of growth rate of people, instead of total change over time, it's just total change, kind of like a net change, right? It's kind of like net profit, where you take your gross profits and you subtract your costs from it. Well, in this case, you take your gross profits, i.e. your birth rate, and then you subtract your death rate from it, and that gives you the overall growth rate. So for any particular organism, really, in any given environment, the carrying capacity we define as the maximum sustainable population. So that means just the largest amount of those things that the environment that they're living in can support, whether it's bacteria on a petri dish or wolves in Yellowstone or human beings on the planet Earth. They all have a carrying capacity. So another example, in 1950, the world birth rate was 37 births per 1,000 people, and the death rate was 19. By 1975, the birth rate had fallen to 28, and the death rate to 11, right? We're getting better with medicine and things to make us live longer. So now we can contrast the overall growth rates in 1950 to 1970. So very simply, in 1950, we had, right, 37 over 1,000 minus 19 over 1,000 basically left us with 18 over 1,000, or 1.8%. Do the same thing with the 1975 numbers, and we get 1.7%. So the overall growth rate barely changed because even though the birth rates went down, so did death rates. Now, when we talk about logistic growth rate, when a population is small relative to the carrying capacity, right? So we have a very small population in relationship to how large the environment can handle. Logistic growth is exponential with a fractional growth rate close to the base growth rate of R. As our population approaches its carrying capacity, so you can see as our population and capacity get to be the same, then this gets closer to 1. 1 minus 1 becomes 0, right? And our logistic growth rate approaches 0. So the fractional logistic growth rate at any particular time will always depend on the population at that time and the carrying capacity, and then of course the base growth rate, how fast that population of things, whether it's bacteria, wolves, people, whatever, is growing. How about exponential versus logistic growth? You can see that exponential growth just keeps growing faster and faster and faster. This blue line just curves steeper and steeper and steeper, and it's growing faster and faster and faster, right? Because the steepness of the growth rate, the steepness of the line tells you how fast it's growing. So as the steepness, right, as the slope, sorry, gets steeper and steeper, closer and closer to vertical, that just means it's growing faster and faster. Now, logistic, you might be thinking, it sounds like logarithmic, and it's kind of close. Logarithmic is actually the inverse of exponential, right? Exponential grows really, really super fast. Logarithmic, being an inverse, basically starts off super fast and then levels off. So logarithmic growth looks like this, and it levels off. And you can see that this portion of the curve looks logarithmic, but this portion of the curve is kind of acting exponentially, right? It grows really slow and then it starts to speed up, and then it gets to a certain point and it starts to curl back over. And that's why it's called logistic. It's semi-related to logarithmic growth, but it has that carrying capacity which makes it level off. It can't just keep growing infinitely, right? Bacteria will grow exponentially until they run out of their growth medium, basically their food source. And same thing with, deer and elk and antelope and all these grazing types of animals. Those herds will grow exponentially until they run out of a food source. And human beings are basically growing exponentially as well, but we're going to run out of food sources and land and all that kind of stuff. So that carrying capacity is going to turn our exponential growth into more of a logistic growth. At least that's what people predict. Okay, so if we go back to examples with global populations. Back in 1960, when the growth rate was about 2.1%, the population was about 3 billion. If we assume that these growth rate and population values represent one point in time on a logistic growth curve, with a carrying capacity of 12 billion. So we're basically assuming that the Earth can only handle 12 billion humans. We want to know if this model successfully predict the 2013 growth rate of 1.1% given the 2013 population of 7.1 billion. Basically, we want to see if those numbers would fit a logistic curve. Well, we can figure this out by starting with the 1960 data to find the base growth rate R in our logistic model. And that should confirm if things work or not. So the growth rate, R is just, if we go back to the formula up here, if we want to solve for R, can you see how it would just be logistic growth rate divided by this weird stuff in the parentheses? So that's all we're doing, is we're taking the growth rate and dividing it by all that stuff that's in the population. So put the growth rate in 1960, which we know, put the population in 1960, which we know, put the carrying capacity in, which we know, and then we can solve for R. Here are those numbers. Growth rate of 2.1%, 0.021, right? 3 billion people, 12 billion is the total carrying capacity. Simplify that, and then 1 minus that becomes 0.75. Take that, divide it by 0.75, and you get 2.8%. So now we have R equals 2.8%. Go back to our original formula. All right, we'll go back up here so you can see it. logistic growth rate equals R times 1 plus population over occurring rate, right? So our 2013 growth rate should equal these numbers, the 1 minus how many people we have over our, how many, what's our total carrying rate. We're basically just redoing this bottom piece, which becomes 0.011 or 1.1%. And this logistic model successfully predicts the 2013 growth rate of 1.1%, right? And that means that we tend to have a logistic growth rate. Now, even though the model works, our population has not been following logistic growth over longer periods. It seems to look like it in small spurts. And you get these types of things: overshoot and collapse. And this type of overshoot and collapse phenomenon happens a lot in the natural world. These are just models, and models give you an idea kind of in a snapshot or sometimes over a long period, but the real world doesn't have to follow a model perfectly. And this type of overshoot and collapse happens a lot in nature with populations of animals growing and then outgrowing their food source, and then a large portion of them will die off. That was one of the reasons why they reintroduced wolves into Yellowstone, because the grazing animals would outgrow their food sources and then they would die off in large numbers, which is very unhealthy for the herd. So they would reintroduce the predators, which kill off, the old and the weak and the sick, and it keeps the herd at a manageable size, and it gets closer to this logistic growth rate, which is healthier. Okay, so what is the carrying capacity? Any estimate of carrying capacity is subject to a lot of guessing. You have to take in rates of consumption of all your available resources and demands on those types of things, and it becomes a very complex system of equations. It's a very complex guessing game. Here's difficulties of population prediction. And then the last thing we want to talk about is how mathematical models, they're great. They can give us ideas, but they can't really predict things very well. Nobody has a crystal ball. So just keep that in mind, that these are best guesses. All right, and that's everything we want to talk about for population growth.